希特也可以研究完，很消息。
好，研究优点自我上升，对，可以可以。我感觉他是根本睡觉啊，是吧？不知道，我觉得他的作息他是在每天找个随机的时间，然后睡一个随机的场所。所以，是吧？
开始上课。So last week, we learned how to find the solution of Dirac frequency for the purpose to quantize the impact. The quantization of the Dirac inner psi equals to sum of being, because in this case the S is the sum of S is means to take some linear combination of different polarizations. Right? So we have the sum of X. Decompose into the P space, precisely the same as before. We also have APS, UES. First A means the energy module, the first A dagger A. And we'll multiply through this polarization U PS, and then we multiply P plus PS Tiger VP S E V I E. Okay. Very much like the complex scalar. And, you also have the compensation of type R. Conjugate of this one, AP and Tiger, and UPR is e to the IP of x plus B P S V P R S e to the minus I e of x. Okay. So very much like the conversation of complex scalar with some additional polarization structure. Then we have it. Okay? And importantly, we point out this there is an anti-commutation relation to describe the conversation condition. Okay. As equals to E S E Q S Tiger. Anti-commutation relation equals to delta SS 1 to with the third function E minus Q. And with all other anti-commutation relations equal to 0. Okay, so this is the conservation relation. This is the conservation relation. Also discussed the harmonic time order. In contrast to the previous bosonic case, harmonic time ordering, if you want to do time order T for two operators or two fields, say psi x and y, has to be defined into psi x and y x0 minus y0 minus rather than plus y and x theta minus x. Okay. So this is the correct definition. Where in the scalar case, bosonic case, here we instead use the plus. In Fermat case, we use minus. Okay. So we examine why this is the reasonable or correct choice by looking at the Lorentz transformation property of the Dupont functions or the Feynman propagator. If you use the plus, then you get a non-covariant transformation of the Feynman propagator. So if you use minus, you get what? This is and this is consistent. This is consistent with all these. And finally, we compute this correct time ordering psi 0 psi bar x. We obtain the very nice result, which in the P space, the propagator is just the I P slash plus M over E square minus M square plus I epsilon. And in the position space, it will be just the integral, the Fourier transformation. Okay. So this is the P space propagator. This part is the P space. So from here, you can also observe something interesting. So if you, in the scalar case, for example, if you have plus, okay, if you have plus, then under this time ordering T, if you switch these two operator or fields, the result does not change. No? Is that right? In this case, it's not true. Okay? In this case, not true. So we will see this effect in the calculation of the issue. The effect comes from here. There's a minus sign here. So up to now, we can summarize the quantum electrodynamics lemma story. The photon propagator is given by this minus I T mu nu over E squared plus I epsilon under the gauge choice XC1. Okay. And for this fermion propagator, we just obtain this is IP flash plus M over P squared minus M squared plus I epsilon. Okay. And there's also external. These are the internal. These are the internal. Okay. Internal. Okay. We have to distinguish internal and external. Okay. This is important. Yeah, it's useful. You have to understand. External means some given data. Okay. Internal means some property. So there can be a incoming photon, then because this is the external. So you have to specify the polarization, right? Because it's external. Okay, there's an incoming photon. You have to specify which polarization this incoming photon is carrying. Okay, so this is what we mean by the external data. This is some input to compute the amplitude. There can also be this part. This just means the body part of this Feynman graph. Okay, Feynman diagram. Okay, this is just the body part, and this is the external photon. There can also be the outgoing. We have epsilon mu star. The external line on it's the fermion. Then we can have more different structures. So these are called incoming particles, okay, which we use. Yeah, we as E. Again, you have to specify the speed. This is the external data. And there can also be the outgoing particle using U bar as E. There could be a incoming antiparticle use U bar times P. And it will also be the outgoing antiparticle. Okay, outgoing yes. Now, so today we're going to just employ these Feynman rules to calculate some examples. Okay, example. Because by now we don't, it's just rules, right? We don't know how to use these rules, right? We have to learn how to use these rules. The best way is to discuss the example, specific example. So let's try to use these rules to write down the amplitude result for a given Feynman diagram. Okay, we did it already for scalars. You know, even for scalar QED, but not yet for fermion. Okay, so it looks, you see, as you can see, it looks, including fermion, the Feynman rules becomes more complicated, right? Right. First of all, you have to take care of the spinor structure. Okay. Second, there are, you know, the mixed with the particle, antiparticle, and the spins, those stuff. So you have to really take care. Everything in order to write down in a correct way. Okay. So how to do that? Let's try to find some examples. Before that, let's make some comment marks. The first remark is the bar the spinner always should put on the left. Okay. The bar the spinner, let's say sometimes we don't know, you know, this is just looks a little complicated, but first question you might want to say, where should I put the U bar or U bar or V? Priority is not clear, right? For complicated diagram. The first rule or the first remark is the bar will be always on the left. Bar spinner means U bar or V bar. Okay, we have many bar. Okay, we have U bar or V bar. The point is the bar spinner always goes on the left because the interaction is defined in this way. Okay. You mean by that? Because the interaction is psi bar, A mu, gamma mu, psi. Okay? So you should remember all these Feynman rules originally come from we deal with Lagrangian or action. Okay? Why I say so? Because, you know, following LSD, even though we didn't really discuss the LSD transformation, LSD formula in this case, the momentum space Feynman rules come from the LSD or the position space. Okay. Now the position space Feynman rules come from calculating the correlation function. Okay. All this calculating originally from how you deal with the action. So all the rules have to respect the initial action. Okay. Because in your action or Lagrangian, the interaction curve, only interaction curve is defined this way. Okay. Okay. Yeah. So the bar spinner always goes on the left. If you deal with a vortex, okay, because we know vortex represents the interaction. Okay. For vortex. Because this is the definition. Okay. So let's try an example. Keeping this in mind, try an example. So the first example, or the simplest example, is let's make a graph in this way. Okay. And then let's put the arrow on the solid line. This. Okay. Let's try this graph. And this is the P1, and P2, and the P3. And these are the, of course, these are the photons. Okay, these are the photons. This is the electron. Okay. As you can see, well, you can just follow this dictionary, right? Follow this dictionary. Let's check one by one. So how to understand this one? First of all, so this is the internal line, right? This is the internal solid line. It should be this one, this block. So this kind of internal solid line represents a propagator. Okay, you see. Now about this part and this part, P1 and P3. These are the external, right? These are the external. So for the P1, as you can see, which external? It should be here, right? It should be this one. See this block. This is the P3 should be this one, right? Should be this one. Now roughly, you know, that graph is composed. It's composed of this 1, 2, 3 is blocks, and there are also photon lines, right? These are the things. So where is that? This should some part here, okay? Some part here. So it's this one, okay? So this one. And yeah, let's specify here that momentum direction. The momentum direction is one is Q1. The polarization is the epsilon 1. See mu. Now this is the Q2, and the polarization is epsilon 2 mu. Okay. Because if you ask someone to calculate the amplitude for this Feynman diagram for you, okay, you have to tell him the enough data. Okay, these are the data you have to tell him. Okay, otherwise there's no way to specify because these are the input. Okay, these are the input. So this, because for example, these are the polarization of the photon. Okay, if this photon are incoming, you have to specify which polarization. These are the given data. And these are the momentum, Q1 and Q2. Okay. So I think for this, then it's enough. Okay, it's enough. We can try to write down the amplitude for this graph. Now, to specify more, once someone hands you this Feynman diagram, then you immediately realize that for each vertex there's gamma matrix. Okay, okay. So it's better to fix the gamma matrix first. Okay, because gamma matrix determines which kind of vertex or interaction you should write down. Okay, so let's try to specify the gamma matrix. So this is gamma nu. There's another gamma here. This is gamma mu. Okay, because there are two vertices. You see, there's independent and two gamma matrix. Okay. Now we can try to work it out. Just following the Feynman rules. Last time we also learned for each vertex we have to put minus I coupling times gamma. Okay, because minus I coupling is the constant. So let's first put it in front. There are two, right? There are two. We have to put square, right? Right. Now there are also two gamma matrix. We can also write down. And but point is there's a left or right order. Okay? We should be careful. Now this is the point. What should I write? You might say, okay, let's write some gamma mu. Okay, gamma mu, gamma nu. Okay? You can maybe you ask why guide also doing this way. Okay, this is the question because I have two gamma. Okay, so which one is correct? Now it's come to the that comments, that remarks. The Barlow spinor always goes on the left. Okay. Now let's try to justify which one is correct. Because I already said that this is the outgoing. Okay, this is the outgoing. So this line, this P3, we have to assign some U bar. See, right? Right? And this incoming, we should have a U, right? We should have a U here. Okay. Okay. But the point is, the bar spinors will always locate on the right. Okay, on the left. Sorry, on the left, right? So it's better to put a U bar here. That's the point. So here it should be a gamma mu. This should be a gamma. Okay. Okay. Another quick reason you can argue for why this is the reasonable choice, because this will give you the number. Amplitude is really a number. Okay. Okay. If U bar is on the left, you can easily give you a number. If you flip the order, it's not a number, right? It's a spinor matrix. Okay. So U bar should be on the left. Okay. Now there is a little subtle, you see, because of this. So this formula does not really reflect the ordering of this graph, right? It's like first write down here, write down the structure here, and then going this way. Okay. Okay. So this will be the U bar. Let's see, the momentum will be the P3. So there is a U bar P3, and then there's a gamma mu. So between two gamma matrices, certainly we know there is a propagator. See, there's a propagator. So we should write down a propagator in between. So the propagator we have already worked out. It's just IP2 / plus M. Okay, its momentum is P2 over the P2 square minus M squared plus F. Okay. So what else? So we also have U, right? As said, U has to be here. Okay. As you can see, U is just nearby this gamma matrix. Okay. So there's gamma nu here, so there should be U here. So U should be here. UP1. Okay. Now, is this enough? This is not enough. Why? That's right. Because you have mu new index. Okay, right? Amplitude cannot carry mu new index. Amplitude finally has to be number. So who is going to contract with this mu new index is precisely this polarization vector 2. Okay, so have to write down also epsilon mu 2 q2 and epsilon mu 1 q1. Now I write in this way, single percent, but I just want to keep this upper and lower. This one. And now you're almost done. Okay, this is almost the final result. Except you have to be careful. This P momentum and Q momentum are not quite independent. Okay, are not quite independent. Why? Because for each vertex, the momentum has to be conserved. Okay, all the incoming and the outgoing momentum for each vertex has to be conserved, right? This is a physical constraint. So momentum conservation set Q2 equals to P3 minus P2. See? Because this for this vertex, these are the coming, this is the going, okay? So P2 plus Q2 will equals to P3. Similarly, Q1 has to be fixed by P2 minus P1. Yeah, and that's it. Okay, that's it. This is the result. This is the result. See, because once you plug into this input data, that formula will offer you amplitude result. You see, you'll get a result from amplitude. So this looks a little okay. Do you have any question about this calculation of this very simple graph? Basically, you might say, okay, you're not just tell me some rules for some graph and then just blindly use these rules to get some result. How do I understand this? Okay, you can try. You can try to translate this graph into physical process, right? Into physical process, right? This means there is a incoming particle, electron, essentially. We are talking about QED, and this particle essentially means electron. There's an incoming electron carries momentum P1. Okay, they meet some incoming photon carry momentum Q1. Okay, then they try to scatter, right? Try to scatter. Then the electron absorbed this photon. You see, it becomes another. Okay, becomes P2. Becomes P2, and then emit a second photon. Okay, the second photon carries momentum Q2. Okay, and then it becomes the final electron, outgoing electron, which carries momentum P3. This is the process. This is the process. And now, what's the physical meaning of this result? Okay, the physical meaning of this result is this result offers you the amplitude result of this scattering process. Okay, of this particular scattering process. This is only one diagram. Okay. Well, of course, usually we have to take into account a lot, sometimes infinite. Okay, diagrams, sum them together. But this is just the individual, very particular diagram. This result tells you the amplitude, and we know if we take the amplitude square. Okay, if we take the amplitude square, then the physical meaning of that is the probability. Okay, is the probability. It measures the probability of this scattering process. Okay, so that's the meaning. But this looks too simple. Okay, it looks too simple. We should try some more complicated. So let's try another example. So this looks is quite different from this one, right? It's just looks like a tree diagram, but that's there's a loop. There's a loop. There's a loop that. So how to deal with the loop? We learned how to deal with the loop in the scalar case. Then this way, So instead, if you just follow your dictionary here, try to understand this, then the immediate thing you have to specify is, you see, because this is some incoming, see, this is some incoming photon, okay? So we have to specify the polarization, also momentum. Let's specify. And the momentum is P. And similarly, this is the outgoing photon, okay? So to specify the momentum and also polarization, okay? But because momentum has to be conserved, right? There's only a single particle incoming and a single particle outgoing. it should be the same momentum. Otherwise it's rotating. Okay? It should also P. Okay, has to be P. Momentum is conserved. And the polarization is specified as true. Mu. Now, like before, for each vertex, you have to specify the gamma matrix. Okay. Let's specify the gamma matrix here. So you might already observe some rules, some hidden rules. Like you see, this polarization vector index nu and has to be synchronized with this index nu. You see, right? Because they are putting together. Okay. So they are nearby. So this index are you contract them like this graph. You see, there's nu and we have a nu here. We have a nu here. Okay. Why? It's natural, right? Because for that is that particular photon participant in this vertex interaction, right? So the vertex interaction comes from the definition. The vertex interaction index has to be the same as the index of that participating photon, right? Not some other photon, okay? So the index of the gamma matrix has to be the same of the participating photon polarization index. And we also have a gamma mu here. Here is mu, okay? The mu. Now, what happened for this loop, right? And this is a quick question. It seems some new thing we didn't see before. It's not a big deal. You can build like before. This, of course, is the internal line, right? These are two internal lines. One is here, another is here. You see? For internal lines, the solid lines, we know it describes the propagator of the Fermi. So we have to assign the structure, the Feynman propagator for each internal line. Okay. Now we have two, right? We have two. We have to assign this propagator for the two twice. You have to do twice. Okay. Then, like before, there is some undetermined momentum for the internal loop. Then you have to integrate that because it's not some input data. It's some free parameter to integrate. So and let's try to write down. Okay, done. What is the result? What's the result? So we know we should have I E square. Okay, it's a two vertex. Okay, like the previous example. Okay, to this coupling square. And if I specify this internal momentum as P1 and this internal momentum as P2, then as I said, P1, P2 has to be integrated, right? Right? Eventually, there is a constraint, as you will see. There's a delta function. There's actually only one free moment. We can start from here. You can first write down this kind of integral. And there will be a third function constraints for the momentum conservation, because let's say for this vertex, the incoming is P and the P2, and the outgoing is P1. So there should be a P plus P2 minus P1 third function, okay? And there should be a polarization vector epsilon mu2 star, epsilon mu2 star and P. There should be also epsilon mu 1 P. Now the key question is how to write the result coming from this loop. Like before, let's first specify the mu gamma matrix. The gamma matrix. Let's first specify the gamma matrix. Let's see gamma mu, gamma nu in this way. Okay, in this way. Is that okay? Because previous example we put the gamma matrix in this way. See, gamma mu, gamma nu, and right. We can do it this way. We can put this first. So roughly, well, there's some connection between this diagram and this diagram, right? You can first imagine you cut here. You see, if you cut here, then it becomes that. You see, this final diagram is essentially what you do is you just gluing these two. Okay, just gluing these two endpoints, then you get this. Is that correct? So if you specify the gamma matrix in this way, then there's a clear order. So what addition you have to put is first you put some propagator. The propagator has to be which propagator? This is the gamma mu. This is the gamma nu. So if I try to follow this way, let's say, try to think about this diagram coming from just gluing these two pieces, then we have to put it there. You have to put the P1 propagator in between, right? Like the P2 there. So there should be I P1 slash right over P1 squared minus and squared plus I. Okay. But we do know there's an additional propagator. There's an additional propagator, right? Now we glue them together. It's not cut out, not cut open. Indeed, there is a good propagator. So we can write additional propagator. Okay. Then what we should do? So don't forget, the propagator carries some spinor index, right? Propagator just measures how the spinor propagating to another spinor. Still has a bi-spinor structure. Okay, propagator has a bi-spinor structure. Okay, and this is also matrix. This is also a spinor propagator, and this is a matrix. So putting everything together, this is a sphere matrix. Okay, this is sphere matrix carries the spinor structure. Okay, but from this diagram, we do know forming a loop, the spinor structure has to be contracted. Okay, trace. Okay, so there's only the solid line can carry spinor index. Is that clear? Only the solid line can carry spinor index. Now, all the solid line is closed. No open endpoint. Okay, for the solid line, there's no open endpoint for the solid line. All the solid line closed. So it means that there's no spinor index remaining. Okay, anywhere. Okay, just closed. So what should we do with this spinor index? We just have spinor index. That's right. We have to put a trace. To close this spinor index or contract the endpoint spinor index, by definition, we have to take a trace, right? You can check yourself. You see, that means the spinor index contracted over. Okay. So then this would be the correct result. So now for the final, if you arrived here, then you can justify back. because there's a cyclic property of the trace, okay? Does not really matter. You write this as gamma P1 slash gamma P2 slash or P2 slash in front gamma, then P1 slash and then gamma. It doesn't matter because if I have a trace, in my trace there are matrix, and I can cyclically permutate the matrix, okay? The trace does not change, okay? This is some mathematical theorem, okay? So it means the really important thing is the cyclic order, okay? It doesn't matter really right basis or just cyclic permutation a few times. It doesn't really matter. The result does not change, okay? Does not change, right? Is that clear? Right. For example, I can start from any point because I can start from this gamma matrix. Okay. Okay. If I put everything correctly, then take a trace, it will be the same as this one. Okay. Okay. For example, I can cyclically permutate shift this gamma mu here to once permutation, and then in the end, and I make a gamma nu in the first. It does not change the trace, right? Because the trace preserved under cyclic permutation. OK， 当我们把这个球基里面的东西做轮换的时候，这个 trace 不变。OK。Now there's. You might say, okay, that's it, right? That's maybe the best you can do, right? Just following the rules. You take care of everything almost. And then you also take care of the contract of the final spinor index. And then it seems perfect. It's perfect. Because this is you perform this calculation, you get a number. Okay? You get a number. But this is not enough. There is some subtle sign here you have to put in front. There's an additional minus sign. There's additional minus sign in order to make this result correct. Minus. Okay, so let's discuss why we should put the additional minus sign in the end. Okay. Of course, people already justify this should be the correct result. With this additional minus sign should be the correct result. People check, examine the many different things to justify this. We know this is correct. Oh. Now let's understand why this should be the correct result. Yeah, indeed, the magic comes from the loop. Okay. So there's an additional rule. Let me first put the rule first. So the rule is the first important thing here. For any fermion loop, there is a trace. Okay, and importantly, the trace is over. The first comment is for the trace. The trace is over the spinor index. Okay, so which trace you are talking about? The trace. By doing this trace, we mean trace over the spinor index, meaning that we take the object inside the trace as a matrix in the spinor index. And the second comment is we have to put additional minus sign for each fermion loop. Now we have to understand this one. Now, does anybody know where by just following the rule we just employed? Can you see? Is there any place we missed a minus sign? Can you guess? Can you see? Is there any point that we miss the minus sign? Or just naively following all these previous rules? Okay, all the previous rules. Where is the minus sign we potentially missed? Okay. Where it comes from? The minus sign comes from the fermion propagator. Okay, the fermion propagator. Because in this rule, for both P1 and P2, we just employ the same fermion propagator. You see that? Right? For P1 and P2, we use the same fermion propagator, but just replace different momentum, right? For the first, we use momentum P1, and the second one, we use momentum P2. But if you think about it carefully, this is not quite right, okay? Why? Because as said, to put everything correctly, first you have to respect the coupling structure for each vertex, okay? Which means what? So let's talk about this vertex, okay? For this vertex, if this nearby upper solid line you assign with some psi bar, then this lower has to be psi, no? Right? Because this coupling is always a psi bar A mu psi, right? You cannot put two psi bar, okay? Doesn't make sense. Is that correct? Okay? If you realize this, then it means that if this propagator is the psi to psi bar, then this should be the psi bar to psi, no? Is that right? Okay? Is that clear? So if you define this as a psi to psi bar propagator, then this propagator has to be a psi to psi bar. Okay? Not quite the same. If you switch psi and psi bar, there is additional minus. Okay? But here we didn't take into account that. We just say, okay, let's try to make this rule very, very simple. For each internal solid line, we just put straightforwardly the same propagator without the additional minus sign. Okay? And assign the correct momentum. Okay? Assign the correct momentum. Okay? That's it. But as we saw from this definition here, if you switch psi and psi bar, there is additional minus sign. Okay, is that correct? Now you try to challenge me. Okay, what are you talking about? What you're saying is from the argument from their position space 2-point function. Okay, but here, what we're really calculating is the amplitude. So for amplitude, there's no meaning to assign some positions from x or x1 to x2 because everything is in the momentum space, right? You might ask in that way, but we can go back to the original position space, okay? From same graph, right? That's what we did for scalar. So we can do ASD transformation to get this momentum space Feynman rules from the position space Feynman rules, right? Still, there's a minus sign missing there if you go back to the position space. So to see this minus sign, the best way is you track this sign, whether this sign is correct or not. You go back to the position space, okay? Just track back, okay? Go back from LSD, you can get it here. You can also go back to the position space. Then it's very clear, right? Then it's very clear. If you think about the position space, such kind of diagram, it's very clear. You have to include the additional minus sign, okay? Additional minus sign. Why? As said, in order to respect this coupling structure, okay? In order to respect this coupling structure, for each loop, the line has to be carry a relatively minus sign, okay? for this uptake lower propagator. Okay. Otherwise, does not make sense, right? Otherwise, it does not make sense. Because if we put every propagator, let's say from sidebar to side or side to sidebar, then it does not consistent with this vortex. The vortex has to be carrying the sidebar side. Okay. So if one is side, another has to be sidebar. Okay. Okay. This is the quickest way to see why there's a missing minus sign. But if you read textbook, there's a lot of discussions, different, maybe 10 pages, how to explain this minus sign in many different ways. Okay, you can try to justify and find different means. Okay, so similarly, there's also a minus sign for if you exchange the minus sign for interchange of external identical fermions. But this case is not quite often. That's bounded by this. Just mentioned. This is essentially for the same reason. Okay, for the same reason. It says that if you interchange the external fermions, then you have to put the additional minus sign. Okay, essentially the same reason. You see, because we know when you interchange two fermions in the position space, essentially means that you switch. Okay, you switch two fermion insertions in position space. Okay, okay, because of statistics, or as we mentioned last time, if you switch the order of the fermionic operator, okay, there will be an additional minus sign. That's the origin for the last minus sign. Okay. Therefore, by including this minus sign, you can try to simplify. We know this is the correct graph. This can be simplified. This is a double momentum integral and with the dirt function. We can try to simplify this one. Let's say we can try to reparameterize this momentum as k, for example, and then for the conservation, this is p and k coming. The outgoing has to be p plus k. Okay. So in this way, we simplify the result. This will be equal to E squared epsilon mu star epsilon mu 1 integral single integral over A and take a trace from the gamma mu I p slash A slash plus m over p plus k squared minus m squared plus 9 epsilon gamma mu t squared minus m squared. Right. Okay. So this is the result. This is the result. Yeah, these are a few simple examples. You have any question for this two examples? One is a loop, another has a loop.
Is the trace here the partial trace?
Trace here is
Partial trace.
partial trace. No, it's just an ordinary trace. These are the matrix in the spinor index space. In the matrix, the trace is just take the in that matrix the trace, just a simple trace, usual trace. It's no fancy addition. Any other question? Okay, so next we're going to see a few more examples, like say 2 more examples. Let's see, maybe we can have a break because these 2 examples we want to discuss them together. Yeah, let's have a break. 15 minutes. Right,这个没啥入。对，你有没有被退烧？就是两个可以说两个名字嘛，这样 A 我就选一个，你把这个实际上我们这个gam嘛，它实际上是有3个指标，他说就连我一个鼠标都要还没有，如果我从现在是从小做起的，如果说从网上数是不是有点C？不看的话，是不是就是要又是个主角嘛？我这边这个主角，那边这个。然后对这个四人四局，买的电脑实际上是有物理。这里其实很多，看那个还没写代码的。我们这个反的箭头，算出来到底是个40个，对，这个代表他写的时候，你看他是可以表示跟这个是数学。不是你两个像，我一定要自己往视频上，必要加持，要6指标。哦，字标来过，为什么？那个有这个意义是而且那你最后这个短视频完全它这个 flow 的感觉跟你不能过它这个 flow 的感觉是因为这两边线它球所以说你需要让自己这个圈点这个写这种哦，你要跟那个 trace 对低调这个的话，如果你是对反粒子的话，它那个要不能往那个方向。这就是打断的。也看不出来是他的。你要发小的，上面是关的。是没有。上面那条线是反的，故意就对下面那个，它只是这个反适当的也是一个路，因为它必须要保护，你不想对，它要保护。我们没有两个题在后面写的，那我是白，它对，它都看不懂。哦，但是就是你绑在里面，想象都是。
这些是
约定具体说，
我们在这些让我看一下，
但是现在刚才那个同学问的非常好，那我可以说，我可以把劝你。就他问你两件，正好这样子，发出来的电子
这个拜是看，就在这个中间。
肯定是如果你这样取规则，肯定都是稍微发点 flow， 那你相当于光规则。
你去拿这个速率的方式，
你还是
哦，这个是负电，这个是正电子，是因为这个地方，因为这个又是怎么看的？ 哦，就沿着实验室。
外，因为标上没有它那个光子，没有线，但空出来这个就是
对，
就是反粒子，就是对比就是中子，
反粒子是反粒子。
Galaxy 其实不完全，像昨天 Galaxy 也对它这样子，这个这样子嘛，你要不让你外三本身就不存在键头的问题，出去比较重要，出去的分辨率是好，出去的是没有。
这个电子
都是我里面是外部线，这里它另外内部线。
我感觉你一天不值班了。对，
所以这个这个时候，
我昨天就是358
一个正常的一个负面的，
我感觉按照时间来反应早饭。
对结论是吧？
那个晚饭，我们结完，我昨天就是第二饭，
网友就没有那个
10点半，这个10点40来。8点半，
这个两个多晚上，跟这两个交换，这个同时，你看这个同时，这个到这连算的是这个。
我先就说为什么老按说，他们3楼脚踢飞了，就
好，这就需要给别人
他们那晚在脚步下，
又做了一个脚不需要的，
就2张，因为说出来要
那个其实就是上去的。
好，什么不行没法影响，这样就
对，你想象整个的话，
我觉得我是，
那这谁证得出来？
你又不退的话，那最后你又看也相当吧？一个简单非常多的题，为什么要让纳税？为什么就假如说这两个做个简单的题的话，我就会讲，
但我不知道他那个
要被敲打。然后他得这样说，老师就是这里为什么要取 trace 还是什么？
还有一个呢，
一个直接把它写别人应该
那边多点是好。
就是矩阵向量边的矩阵多项，可以把它死边的应该全写。
对，
可以的，它可以全写。
谁做的啊？会这么一道？
回答
这是想用的，
直接等于
让人讲加了哇。
矩阵传递就是一代。
哦，有国评老离谱了。最后这个后来最后是真正的，
不是，他不是最后，他就他 point 是因为这个这个 solid line 形成了一个 loop，
太少了，不注意这件事。
loop 接完了，
对，他
这边的 index 应该消失，所以最后有一个阿尔法，
说明他活得多。
阿尔法的成人的。
这些帮助不是。他活得短一个是吧？
你也可以的，
这是10分钟吗？
因为毕竟不是最后是有个阿尔法
两个历史
对应很多这太危险了。然后到最后这个矩阵，
阿贝尔也
矩阵你最后
阿贝尔那种
矩阵也有因在里头，最后这个矩阵的因在里头。
阿贝尔活的也不错。
还有一个人讲那个，就是讲网络。
定义就是
听不懂，这知乎上最
矩阵
他说抄的一个什么时候？老师当时一直质问讲，安标就是啥？安标就是啥？在知乎上
就举这个，
是吧？
粤语我当时也不清楚。
阿尔法贝塔，
那个直接维基百科上查，他能问我细节，你怎么知道？我操！
你在做表想就
你会德语？
line line 是它有两个，有一个 double 一个。
太紧张了，
这个实现是吧？
太恐怖了。
是有 parry 的一个矩阵，可以用一个三角方，然后最后你要 point 你要最后定义嘛，这个指标是这个定
你的不是，你换个对称变换调整自己，如果调整条是上面好，这调整
在标的形状。
它自己发生，如果调态条里面有它有没有 F 有没有这项等于零，一个调态 F 做一个起变，它就变零，那就做定锚了。你上直接维权。
第一片的是，
就是你
第二个是
真正
自动氧没有去，
但是你那个不是调态，很好，
做完，
而且你知道
咱不
现在那我这看这个情况，不是说不算是
三半人这样换。
如果做那个英文这里的有应该是会有它
但如果你
这个第二是你在现在是这样的话，完全都是不会选它这个是一个新的那个
你如果抽取就所有
中间它中间是个，
那其实就这老三百
你可以这样到这儿来看，你把这个看拿出来一下。
这种理解我。
这个不用，有一个出路，可以学习通路，就堵死了所有人开发别不偏题。
看这个规则，
人类的资源就不用
看这个规则，
它能够裂开，就有这样的回去。
这个答案应该在。
就小组
让你这个搞一个东西，
答案应该是
它的意思是
的它那个不一样，它的不是
认为的一个定理，它的意思
前面。
它的意思是大家全都能把你一个产业
就是觉得
这个的话，用的是两个加材料相方法，一个是二这样，这是反正。如果按这一个的话，一般来说是密码，就它它的就是就是说你先说你去搞这个算先不管下面的，你从那个分解这一是快变换的标准。这两个的话，你调态要两个所谓的这个相对调态就 A 层 B 层
因为我他的这个全脑的支持我都一直，他全脑和你给他全部
只有你只有我们两个
一平他有点表，
然后呢，第二个就是
因为你本身
要我要传递的信息，然后不管现在我网上已经发了一个，
另外一个说法就是霍伦兹式，可以在每个4个然后他
然后只有我们两个操作，
那接他把结合
是一个是这样，
因为在
就他那个那边要去
那偏正可能
因为手上有，如果他是去实在是如果那个的话，
你把它当成
也肯定要，
你可以把它当
10
成
位可还是少了，
优异，
如果再多两次，可能分级是
这是自学是吧？
就是
自学一2年吧，
自学
我会把它说往我的个人实践里面继续人感冒，
是，
我还要把它发
这样的话你写出来一个就是一个 skater， 那个参考
啊，
他这么学，
你会成一个你
这个是用对吗？
他讲他
但是你知道在公司里可能只有那个啊，为什么能对？
为什么跟他对？这个不是就是你 trace CUE 吗？CUE 不就是2个外子的箱子上了吗？
你 trace 就没有人给我定义过，从来没有人跟我讲啥是定义。你要是 trace 啊，要是不 trace。
又不用你告诉分家
就难。那你上个屁！我说出生你长狗屎，你看现在你觉得他狗屎
啊，这个
觉得跟出生你什么都不行。
矩阵首尾相连，
把这3个做的指令怎么变？
你说的是这种，那个。
对，因为不像话，如果他这个东西呢，
不是你过来，你觉得你主要我一想就不是讨论你这个要放在心里上，就把它跟我说，一个思想带上去，这个一根线，还是一个共振，
我要转一圈的话，
还有共振，
最少最多
算你强迫
但你要把这技术点啊，它可能挺好，
但是让它翻转一下，不会过来的。就你去拼3个月，少2个多月，差不多3个月，在2维上都可以。真奇妙，按照
你的问题理解了吗？
OK 的。
Let's continue. I think we have a lot of stuff covered. So let's continue to discuss the example. During the break, ask about the trace. Why we take the trace in the end? I think the key point is in all these graphs, in all the examples, when we talk about gluing two solid lines, by definition, we're doing one index contraction. Okay. And in the end, we form a loop that's also the same as just gluing once more. Okay. Then we have to do the once index contraction, and the last index contraction is equivalent to take trace. Same thing, right? Because one index contraction means matrix product. You take a matrix product, do one index contraction. So the next example is more close to the real world, the real meaning. In the real world QED, okay. We're going to discuss 2 more examples. Okay? 2 more examples. First one is the E plus, E minus. Do you know what E plus, E minus means? Oh, that's right. Scatter becomes the mu plus mu minus. Do you know what mu means?
Mu and
yeah, this is a muon, okay? Muon is one type of particle in the standard model, okay? So do you know the difference between muon and electron?
mass, and the first is the first generation electron, and the muon is the second generation.
Very good. So muon is some other particle, but very much like electron, okay? If you only talk about the QED property, meaning the electronic property, then they are almost the same. But the difference is the mass. So you can think about the muon is some kind of electron but with quite different mass. If you only talk about UED. Okay, so this is quite a real example. So how to make the graph? So let's specify the scattering process this way. Let's say there's a E plus E minus. This is E minus and E plus. Be careful. We in the QED we think E minus is a particle and E plus is antiparticle. Okay. So this should go this way. This should go this way. And, they can collide and it becomes a photon and then decay into, let's say, mu minus and mu plus. Okay. So similarly, mu minus means the muon particle and mu plus means the antiparticle. Okay. Okay. As said, as promised previously, because now the external line now is includes some antiparticle. Okay. So the particle flow direction looks a little weird, right? Because this is not the motion, direction of motion, right? So we have to specify additionally the momentum. Okay. So let's specify additional momentum, P2 in this direction. And this is the momentum direction, P4. Okay. And if the momentum direction and the particle flow direction are the same, then we don't need to specify additional. Okay. So this is the P3 and this is the P1. Okay. Then this diagram.
右下角接图高。
I'm sorry. Okay. Thank you. Because this is an antiparticle. Okay. This is an outgoing antiparticle. Okay. Antiparticle. Then this makes sense, right? In both ways. First of all, it's consistent with our rules. Okay. Our rules for particle and antiparticle flows. Okay. Second, consistent with the physical scattering process, right? Because this in the physical momentum, there are just two incoming particles, the two incoming objects, okay, collide, then become two outgoing objects, okay? Okay? They consider with both of those. The payment is we just we need to put some additional. And the second process we want to discuss is the E minus mu minus goes to the E minus mu minus. Okay. Clearly, we don't become some new particles, right? You see the same. Because E minus mu minus become E minus mu minus. So this means the scattering process looks like exchange some particles, exchange photons. So going this way. So P1, P3, P2, P4. Now this is the E minus, still E minus. This is the mu minus, still mu minus. Okay. These are the two examples we want to compute. Now, how to compute? Of course, you should try to ignore all the primary rules. Ignore all these primary rules and write down the amplitude for these two graphs. So let's first try the first example. I want to compute the IM. Then I will get, let's say for one vortex, I should put minus I coupling. And let's first deal with this first vortex, left one. Then I should have a gamma mu. And as probably as that, we should put the bar always on the left. So there should be a V bar P2. Okay, you can check. Okay, you can check because there's E plus. Let's check one by one. First, there's the incoming. This one should be U, right? It should be U. And there is a incoming antiparticle. Okay, is this one? You see? So there should be a V bar. Okay, but the point is, bar should be always on the left. Okay, so for the first gamma, we have to put V bar gamma U. Okay, like that. So we have to put V bar E2 gamma and U U1. Okay. And in the middle, you have to insert a photon propagator. See? Now photon propagator becomes the internal line. The photon becomes the internal line, meaning you have to put a photon propagator. Let's first maintain this coherent form. This will be the photon propagator. And then afterwards, deal with the left-right part. There is an additional vortex. We should put a minus on coupling. And then there is a U bar. So for the right part, there should be a U bar P3 in the gamma mu V P3 P4. Okay. So this is what it is. Okay. Yeah, it's not difficult. It's just that's it. Okay. That's it. Okay. Yeah, it looks a little simpler than previous examples actually, because in this case, actually you only thing you have to prepare is about each part. Each part. Now for this part, you get a number. Okay, you have bar gamma matrix U. The bar gamma matrix U. You have a U bar gamma matrix V. Okay. Then you get a number, and then in the middle you have a number. Okay, a number. And as you can see, the mu index also, the mu index in this case is contracted with this photon propagator mu, right? So it's contracted over. That's it. Okay. There's no magic ordering or subtleties here or additional science. Everything is simple. Okay. This is what it is. Now, we do have some interesting observation out of this result. Let's see what it is. So because of momentum conservation said, so if this is my K, okay, this is my K, then clearly K equals to P1 plus P2, also equals to P3 plus P4. Okay, as a vector. Okay, because momentum conservation. Also notice for the external lines, the spinor external line has to satisfy the equation motion. Okay, because they are on shell particles, right? Mentioned before. So because of equation motion, we will have P1 slash U P1 equals to MU. Okay, this is just equation motion, right? This is for U. Where is U? U is the E minus. Okay, left E minus. Okay. And we also have the V bar P2 slash equals to minus M V2 P2. Okay, this is also the equation motion, but for the E plus with momentum P2. Those are the external particles. Satisfy the equation motion. Therefore, because of this, so we will have U bar P2 gamma mu UP1 K mu, because K is the P1 plus P2, we can split K. So this will be equal to U bar P2 gamma mu P1, right, which is P1 slash UP1 plus V bar P2 slash UP1. Okay? Clear? This is from the momentum conservation. Okay? Okay. Then let's plug in these two equations to here. Okay? The equation of motion. Then what you will get is this M V bar U P1 minus M V bar U P1. Okay? Let's plug in. No mysterious. Then what is this? What is this? Zero, right? Then do it the same. Okay? This is zero. Which is very interesting. Why? Can you explain why this is zero? Why this is equal to zero is very good? Yeah, this is gauge invariance. Why? Look, because now we're talking about some physical observable, like an amplitude, okay? Right? This is the final physical observable. It should be gauge invariant. We know the C-dependent part, it depends on the gauge, okay? Now, what I'm now trying to tell you is that if you try to evaluate this part with the K mu construction, meaning if you just try to want to compute this part with this K mu, okay, then you get zero. You get zero. So this perfectly justified the 1 minus C term does not contribute to the amplitude. Okay. I am. Okay. Okay. So we can interpret that this is the gauge invariance, demonstrating gauge invariance. Because I am should be gauge invariance. Okay. So for this reason, then the result, which essentially means this term is gone. This term does not contribute. This term does not contribute. Okay. So only G mu nu contribute. Okay. Because straight away, G mu nu contribute means just did nothing but contract this mu index and this mu. Okay. You see? All right. So we just put these two index the same to the final result. So obtained the final result of I am of 3 erase this So the final result of the M, for example, now becomes the E squared over E 1 plus E2 squared, E bar P2 as that mu P1 mu bar P3 gamma mu V P4. Okay, that's it. This is the final result, and this is of course supposed to. This is of course that's the P squared. Okay, P squared, and we also know this is the by definition this is the TU. This is the S. Okay, so this is the E squared over S. Okay, so sometimes we call this diagram is the S channel. Okay, S channel. This is S. Now let's do the same thing for the example 2. Okay, for the example 2, secondly rules the IM will be equal to similarly U bar P3 gamma U P1 and minus I similarly minus 1 minus C KU KU P1 minus P3 here. U bar P4 gamma U U. So this is the result. Yeah, I'm not now. I will not explain term by term. Okay, you can do it straightforwardly, following the primary rules. Because this is much more simple. This one, there's no antiparticle. Okay, it just exchanges some photon. And that's right. This will be the key. This will be the momentum. Okay. The key is the 1 minus P3. You get this result. And essentially, for the same reason, you can drop this you can drop this gauge dependent term. Okay, you can check it. The amplitude result guarantees. This is this does not contribute. Okay, because again, you can check the contraction with key mu. For example, with this part becomes 0 because of equation motion. Because of equation motion. So final result will become the E squared over the P1 minus P3 squared U bar P3 gamma U P1 U bar P4 gamma mu P2. Okay, you see, there's no antiparticle, everything is U, right? Or U bar, okay? But this is the E minus mu minus goes to E minus mu minus. Now you ask me, it seems you don't distinguish electron and muon, right? This way you see it? Indeed, this is my convention. I didn't distinguish electron and muon because I use both are using U, right? You see, or U bar. But you should keep in mind when you evaluate the equation motion on electron or muon, you should input the different mass, okay? Because they have different mass. Apart from that, they are really the same. So I don't distinguish that, but you should keep in mind. Okay. Okay, but of course, in principle, yeah, yes, yeah, that's what I mean. So now you get 2 results, right? This is the result for the first example. This is the result for the second example. So what's the point? Now the interesting point now is the following. There are very interesting observations. Now, this is IM. IM is not quite observable. It's not quite observable. We're really interested in the M squared. Okay, the M squared. This is defined as the MM dagger. Okay, okay. So we have to evaluate also the M dagger. What is the M dagger? For these two. So interestingly, you can check M dagger also has a very simple structure. So for the first example, M dagger is nothing but E squared over S V bar P4 gamma mu U P3 U bar P1 mu V. Okay, this is the M bar. Now you ask me, how do you know? Simply you just write down it, but how do you know? Well, you can quickly examine if it's true, right? Because you can check. You can check. You can check yourself. In general, if you have two Dirac spinner, you have psi 1 bar, gamma mu psi 2. Okay? If you take the Hermitian conjugate, you can just check it. You can take the Hermitian conjugate of this one after a few lines calculation. For example, this will be equal to the gamma 2 dagger gamma 0 dagger psi 1. Okay? Is that clear? The psi bar is defined as the psi dagger gamma 0. Okay?
Is that an I? Yes. 就那个 m 等于那个 p 减 p3 方分之1方那里，是不是还缺了个 I？
Good question. You should fix it. There's some I here.
Okay.
No question. You fix. So, what is this? So this is the psi 2 dagger gamma 0 psi 1. And this is nothing but the psi 2 bar gamma 0 psi 1. What it says is that we take the Hermitian conjugate of such combination is amount to switch the psi 1 and psi 2. We have the psi 2 bar gamma psi 1. Okay? So you can easily calculate the Hermitian conjugate of this result, right? So this result. Okay. And what you get is the V bar P4 for the last part, gamma mu U P3. Okay. And then for the first, you get U bar P1 gamma mu for the 3 P2. Okay, that's what you get. Now you put them together. You get this one. So if you want to calculate the M square, you get this one. Okay, get this one because you have the result for M. You have the result for M dagger. You get the result for M square. Okay. For M square, you get this one. Need something? Yeah, I see. Good. I think associated with the question whether there's an I or no I here, we can easily see down here. There's a minus I in front of the G mu nu. See? Right? So M will be equals to without an I, okay? Without an I cancelled, okay?
Yes, yes. What's the left view show the right hand?
Right.
Not I.
Right. So this is if the result is without I, then this is the result for M. Let me adjust this. Is correct. First of all, the first result, good. For the first result, this is for M, is that correct? Yes. So the for second, I think there is a IM, but this is for M. Okay. I believe this is correct. Yeah, that's right. And then we calculate the M squared. We get this one. Now you can see the magic. The magic is to calculate this one. We can use some tricks. Okay. Of course, you can see this is that's the 4 numbers. This is a number. This is a number. This is a number. Also, this is also a number. Okay. But you can also view individual element inside this, all the bracket as a matrix. Okay, that's perfectly fine. Okay, for example, this is a square. This is a square matrix. Okay, this is a column. This is a row. Okay, okay. Then you can first calculate something like this two. Okay, it's also fine. Okay? Because there's associativity. Okay? For product, for any product of a matrix, there's associativity. 没有结合律是吧？没有乘法的结合律 associativity. So you can first do it this way or this way, and then you can choose first to do whatever you want, and then you can choose the ordering of your calculation. Yeah, that's the first thing to think about this formula. Second, one can try to perform a spin sum. Because so far, up to now, we didn't specify all the spins, okay? We just hidden. We hide all the spin index. All the spin index are hidden, okay? Here. In principle, these are the Fermi external particles. You have to specify the spin. Otherwise, what are you talking about? Which equal state you are talking about, right? You have to specify. But in experiment, this is not actually true. It's very, very, very hard to distinguish or to measure the spin, okay, of the state from your detector. You do the collider experiment and then you detect some outgoings. But current technology cannot distinguish spin state. That's the point, okay? Mostly they just measure the energies, okay? Okay, if you know, outgoing jets or whatever, just measure as many as you can without energies, okay, momentums. You cannot just measure outgoing spin, whether this particle is spinning up or down. No way. Okay. Okay, we don't have such technology. Okay. This means what? This means you cannot distinguish a different spin state. Also means for outgoing particles, you have to sum over the spin. Okay. Okay. And for incoming particles, for the initial particles, what do? If you cannot distinguish spin, you just treat all the different spin equally, right? You just do the collider experiment as many times as you can, okay? Means what? Means for incoming particles, you average the spin, okay? For outgoing particles, you sum over the spin. Is that clear? This is what you do in the real experiment. Okay, that's the best thing you can do so far. Okay, so that's one comment for how to deal with the spin. Okay. So suppose spin It's not measured. Can't measure spin, okay? So we can perform spin sum. For example, for mu plus, where is my mu plus? Yeah, this is the mu plus. We have sum S V S V bar S. This will be from the spin sum formula. We will have this equals to P4 slash minus M mu. Now we denote that this is the mu mass. It's not the electron mass. It's mass here. Okay, matrix. Okay, this is the matrix. This is the matrix. Now for mu minus, similarly, the spin sum will give you u plus u bar plus will be equals to the P3 slash plus M mu. This is also a matrix. Okay. Okay, so because of these two, okay, now maybe so we want to, because of these two relations, if you, yeah, we want to calculate some, we want to calculate some combination. But using that result, we can simplify the original amplitude result. Because of that, when we compute the sum, that's time, with real, with different things. U bar S prime P3 gamma mu V S P4 V bar S P4 gamma mu S prime P3. Then because of that spin sum relation, one can check this is the few steps. This will be the trace P3 slash S for mu bar gamma mu P4 slash minus mu mass gamma mu matrix. Take trace. Okay. Okay. Just plug in these two, and you can check this equation. This two. So what? So the point is, previously we ignored the spin. We didn't specify spin. Now we want to take into account the spin sum. Okay, meaning that first we have to blow up the spin. We have to turn on the spin index and then deal with the spin sum. Okay. The reason is explained. Okay, because from real experiment you cannot distinguish. If you cannot distinguish, you should sum mode. Okay, so sum mode. But why we care this particular combination? Why we care this particular combination? Why? Because this is essentially this part. Okay. This is essentially which part? This is essentially this part. You see? Is that correct? This is in sum for this part. Okay. And this four part, there's no real ordering for this four because all the bracket is the number. You can just switch it whatever you want. Okay. Individually, these are the numbers. So I can try to choose first to calculate this one, then calculate the first and the last. Okay. Okay. And for the first and the last, you can play the same game. Okay. You try to turn this block. Try to turn this block with the spin sum into some result. Looks like this. Okay, looks like this. So here we justify that right. This purple line indicates the part with the spin sum equal to this one. Okay, so this. You can do similarly for the remaining part, which is this, together with this one. Okay. You might ask me why do you can just switch the order? Because these are just numbers. Okay, as I said, these are just numbers. So with that in mind, we can really claim if we do the spin sum for the m squared, then what I get is this one, because this is a square. E to the fourth over s squared. So the first trace is coming from the P1, P2 particle, which is the electron. So we indicate this is the mass of the electron, it's not zero. Okay. And in the gamma matrix nu P2 slash minus electron mass in gamma mu. This is the first. Second, another trace. This is the okay. And we'll repeat. P3 slash plus m mu gamma mu P4 slash is precisely the same. Minus m mu. Okay, so this is the final result for m squared with the spin sum. Okay. Now, as you can see, we sum we does not in this case we even does not distinguish the incoming and outgoing. We sum over all the spin. Okay, we sum over all the spins. Now. Because as said, for the incoming spin states, in the real experiment, we actually averaged them, not sum. But for outgoing, we summed. Okay, but at this moment, we sum over average. You see, sum over average. So in order to take the average for the incoming, how many states we have? We have two, right? You see. You see, in each case we have two incomings, right? Each have two spin states, right? Right? So if you sum over everything, you're over counting. So we have to take a quarter. So the true experiment, we have to multiply a quarter in front. Okay? Because we have 4 spin states for the incoming particle. Okay? Okay? But this result is for you spin sum both the incoming and the outgoing. But we do know for the incoming 4. So we over counting by 4, factor of 4. You have to divide by 4. Divided by this 4 means we treat the incoming particle as average, not a sum. So now there is magic. There's also a long calculation here. I suggest you do yourself. There is a trace. Looks a complicated trace. There is a trace times another trace. Okay, as you can see. Okay, as you can see, and with some index. Now, to simplify this, we have to employ trace identities. There are a lot of trace identities. Okay, I encourage you to simplify this yourself, and the final answer of this will be the 32 e to the fourth over s squared p 1 3 p 3 4 plus p 1 4 p 3 plus m mu squared p 17 plus m mu squared p 3 4 plus 2 m mu squared m mu squared. This will be the final result. So what do I mean by P1, P1, 2, or 3, 4? By Pij, we mean the Pi dot Pj. Okay. This is the convention. Okay. This will be the final result. Okay. Now don't forget these STU variables are intrinsically related to this P1, P2, P3, P4. So you can write this alternatively in terms of STU variables. You can write this STU variable, right? So in terms of STU variables, STU, this will be equal to eight e to the fourth over s squared, e squared plus u squared plus 4s mv squared plus minus 2 m squared squared. Okay. This will be the final result. In terms of STU. Okay. In terms of STU. In terms of STU. So this is for the example number 1. Okay. Similarly, for example number 2. I'll just show you the final result. So for 2, the beam sum of the m squared, which is the m prime, distinguished. The intermediate result or the trace result, we have a trace result here, right? That trace result is, for example, 1. Okay? That trace result is, for example, 1. Now, for example 2, you have e to the fourth p squared trace p1 slash plus me comma mu p3 plus me comma mu. Another trace P4 left plus mu gamma mu. There are many mu's, but different meaning. Okay. Mu gamma mu. Okay. So even without calculating this trace using trace identities, we can observe some interesting relations. The interesting relations observation. The observation is, if you try to build up, connect the result of 1 and 2, you realize that the only thing you need to do is you replace P1, P2, P3, P4 by P1 minus P3, P4, and minus P2. Then you get the result 2, number 2. As you can check. Let's check it, okay? What I mean is this one go from this to here, what you need to do is you need to replace P2 by minus P3, okay? Okay? You need to replace P3 by P4, see? And then you need to replace P4 with P4, I'm sorry. You have to replace P4 by the minus P2, okay? By minus P2. Then you get the result number 2. See? Now you say why there is a S squared and a T squared difference. You can check. This rule essentially switch S to T, okay? Or send the S to T. Because S to T U are defined by P1, P2, P3, P4, okay? So equally, this means you send the S to T, and you send the T to U, and then you send the U to S. Okay. So you get it from the example 1 to example 2. Okay.
Sorry, what's the definition of STU?
T is the minus number.
P E minus.
We learned a few weeks ago. It's the minus number in the STU channel. We put it here. Okay. This is the S, okay? S is the P1 times P2 squared. Okay? This is the S. Now what is P? T is P1 minus P3 squared. Okay. This is a very interesting result. This result says that even seemingly very different scattering process or Feynman diagram, they could be related, simply related, okay? They could be simply related, meaning that if you know the result of one diagram, if you know the connection between the two, you don't need to calculate the number 2, okay? Just get the result, which is correct. Correct. Yeah, sometimes this refers as a close relation or estimate. And this is very common in the amplitude calculation community. Okay. Indeed, we have a lot of such kind of relations. Okay, these relations connect different scheduling processes with different estimators. Okay, in a very simple way. Okay, you can justify yourself because this is an easy relation, right? You can even read off this connection from the diagram. Okay, because these both diagrams obey the same rules. Okay, so we make this graph by following the same rules. Now, just by observing these two graphs, you can observe that relation, right? See, the relation says that for these two graphs, what you should do is just try to connect these two. Okay, what you should do is you should keep 2P1 the same. Okay, don't touch P1. Let's start from the first graph, try to get this second graph, okay? By some manipulations, okay? By some massage, flip, momentum, whatever, change, switch, whatever, rotations. Okay. Let's try, okay? Don't touch P1, yes, indeed, P1 does not touch. The line are the same, you see? Okay? What do we do for P2? Change P2 to minus P3, okay? Change P2 to minus P3. You see, this means what? This means we flip this line, okay? We flip this line to here, okay? We flip this line to here. So we change P2 to minus P3, okay? All right? If you flip this P2, then because P2 is coming into this graph, however, P3 is outgoing, okay? So there's a minus sign difference, okay? So you should connect this line with this line, okay? Okay? Now what happens for P3? For P3, you have to change it to P4, which means you have to connect this mu minus line, P3 here, okay, to P4. Good. Okay. Then, yeah, you flip this to here, and then you flip this too, okay? The P3, we're down to P4 here, okay? Because the particle flow error does not change. It's the same mu minus, the same mu minus. Now what happened for the last momentum? For the last momentum, you have to change P4 to minus P2. If you change P4 to minus P2, what did you do? Yeah, means you should connect this P4, this new plus, to here, okay, to here, right? Now, because this is the outgoing momentum, physical momentum, okay? However, this is the incoming physical momentum, you see? So there's a minus sign difference, okay? Now you put everything together. After that switch, and then you reinterpret this new graph, okay? Then this is will be the correct interpretation. This will be the correct interpretation. So this is the connection between these two scattering processes. Okay, this will be the connection for the two processes. Okay, the point is after you massage those momentum, you should not stick to the first interpretation, okay? The physical interpretation changed, okay? As you can see, right? If you stick to the first interpretation, meaning that you still think that this is some, yeah, this is some E minus E plus, then mu minus mu plus. The only thing changed is the momentum. That's not true, okay? You have some trouble. You have to switch. Eventually, you have to switch the new interpretation. The new correct interpretation will be, this is some new scattering process, okay? So this is the E minus scattering with mu minus, okay? The physical meaning is totally different, okay? This is the magic, right? You see, you start from some scattering process. In principle, another independent scattering process has nothing to do with this one, right? Because only the participating particle and the outgoing particle are totally different. How can you imagine they're related, right? They should be totally independent process. But nevertheless, they are connected, right? They are connected. This is magic. The different S matrix for different participating particles and outgoing particles, they are connected in a very, very simple way. Actually, just following the momentum switch, you can connect them. Okay? You connect. So this is the causing relations. It's very interesting. Powerful relations. Sometimes it conceals your calculation a lot. Okay, but using these crossing relations, as you can see, you can just from one result to predict the other one without any calculation. Okay. So indeed, because of that, we don't need to calculate the number 2. We just get the result. Okay? We just get the result. So for the number 2, the final result will be the final result. Simply yeah, I don't need to do any calculation. I just read the result from here. Okay. Okay. Divided by 4 with a quarter factor, then this becomes 2. So 2 is squared. So I change it I change all the others variables. Right? Because S goes to T, okay? S goes to T, and the T goes to U, okay? And U goes to S, okay? And accordingly, you just replace all the variables to get the result. Right? This is important because the simple amplitude result eventually has to be expressed as a function of momentum, right? Right? Always. And also function of coupling, for example. But the dependence of coupling is slightly trivial. Okay? It's slightly trivial. It's just a number, for example. It's just a square or just a power, different power means how many vortexes you have. Simply non-trivial dependence is the momentum dependence, right? Momentum dependence captures the amplitude, the kinematics of the amplitudes, right? How it depends on the motion of the external particles. And now this crossing relation indeed touch this kinematic, this momentum dependence, right? Interesting relations in different graphs. Yeah. They're similar story, but we don't have time. Similar story for the content scattering, but we don't have time. I suggest you do it yourself. It's a similar story. Yeah, you can check yourself. Content scattering. Observe or emit photons. Okay. There's some similar stories for this. There's relations between different scattering in the content scattering. Okay. Okay. So this is the discussion for different relations between different S metrics. Okay, and different S metrics. Do you have any questions about this? Oh, of course, I skipped a lot of details. Okay, this is highly non-trivial calculation. Maybe you should spend at least a few hours or a few days, right? To deal with these trace relations. Okay, there are a lot of highly non-trivial calculations here. Okay. In fact, I mean, there's an entire community of factory, particularly in China. Okay. A lot of young people rush into this community to compute just amplitude, field level amplitude, just compute it. Okay, this is the whole life. Okay, compute them. Okay. Okay, so in the last 20 minutes, we want to introduce some new subject. Yeah, because this semester I feel that we don't have many hours left over. Maybe we have 3 to 3 weeks. Okay, and we have to close this course. But we have a lot of materials. We have to save time. Okay, so do you have any question for the calculation of the QED S matrix? If not, then let's move to the next chapter, which is a very interesting chapter. It's called path integral. Okay. So from now, including the next week, we're going to rush into this path integral. Okay. Our quantum field theory. Okay. So the first question is, what is path integral? First question is, what is the path integral? Is there anyone you didn't hear of path integral ever before? Everybody knows path integral in quantum mechanics. If you don't know path integral in quantum mechanics, raise your hand. So everybody knows. I can escape the discussion of the quantum mechanics path integral. So do you know why we need path integral?
Another available integration. 它可能有3种，一个是矩阵，一个是椭圆，第3个就是
So what is the intuition or motivation? Why we even can think about this path integral? Why this is reasonable? Why this is correct? What is the intuition? Do you know? What is the first intuition? What is the motivation? Why we should think it? This is a crazy idea, right? Do you agree? This is the crazy idea, right? Crazy idea. So where it come from? Where does it come from? Where is the intuition? Hopefully everybody knows this. Having the 路径积分. Okay. Well, the first question is where is the intuition? Where is the intuition? Anyone see some ideas?
Least action principle.
Least action principle? No, that's not
That is
anything else. Where is the intuition? Because it's just says something like we should include all the possible paths, right? What? That's correct. Okay. So the first intuition we learned from classic physics for this path integral is the double slit experiment. Okay. Double slit experiment. Okay. So what this says? It says that if you have a source of some wave, if you have source of some wave, okay, located here, see that, and if I have a screen, okay, so for some reason my screen has 2 holes, okay, here, okay, and I have another receiving screen here. If I want to observe here, observe the wave coming from this edge, okay, in this screen, then clearly there are 2 paths. Okay? Clearly there are 2 paths. Clearly there are 2 paths. This is my observer. Okay, I'm standing here. Observe the wave come from here. Okay, what you learn in your optics. Okay, this is the double slit experiment. So you should take into account these 2 contributions. Okay, one is coming from here, another is coming from here because my screen has 2 holes. Okay, okay. Now seriously, what in terms of formula you should write the total amplitude would be a combination of A1 and A2. Let's say this is A1, this is A2. Okay, this is my A. Okay. This should be a linear combination of these 2. Okay. Now, there's a story included in, by the way, AZ's textbook. You can read it. I'm not sure it's correct. That there's a crazy guy called Simon. Ask a really good question. What if I insert many screens? And at each screen, there are many holes. Okay, so you just push the idea crazily to the extreme. then you realize that all the string is gone. Okay. The only thing you need to do is just take care of all the paths. Okay. So this is the idea for the path integral. It's not a very precise formulation, but it's a very good intuition. Okay. Come from here. Okay. Come from here. Come from here. So the idea is as follows. What if insert many or infinite many screens plus infinite many holes? Okay. Then you realize the screen is gone. Okay. The screen is gone. So you have to take into account all the paths. Yeah, that's what you have to do. So all the paths contribute to the amplitude. All the paths contribute to the amplitude. But as I said, this is, of course, this is not a precise formulation. It's just some ideas. So we have to formulate this in quantum mechanics. So this is the thing we want to discuss in the next 10 minutes. Okay, 10 minutes. In the next 10 minutes, we want to review or remind you how we obtained the path integral formula in quantum mechanics, as we always did previously for harmonic oscillators or for many other examples. Okay, so let's talk about path integral in quantum mechanics. So let's ask a precise question in the following way. Okay. Question is as follows. So this is my time. This is my time. Okay. It's a little weird error, but that's accepting. I have some initial state located somewhere. So this is my time, and this is my x direction. Okay, in my x direction. Suppose I have an initial state located at this xi. Okay, and at some beginning time, let's say ti. Okay, so I have a position eigenstate of a particle. Okay, start from here. Now I want to measure at some final time tf. Okay. The transition amplitude to another position, which is xf. Here. Okay. Here. So what is the transition amplitude for my particle propagating starting from this position to this position? Okay, and from time ti to tm. Okay, this is the quantum mechanics question. You should be able to calculate it, right? If you learn the quantum mechanics, right? This is a very precise question. Okay, this is a very precise question. Now, how to calculate this one? To calculate it, you have to specify your Hamiltonian, right? Because we know Hamiltonian does the job to take care of the evolution, time evolution, right? So you have to take care. You have to specify the Hamiltonian. So suppose my Hamiltonian is this way, plus some potential is an operator, right? Now I start with the initial state, which is the position eigenstate, okay, at ti, and up to or propagated to the final state, which is the f state, which I call this is the xf eigenstate at tf. Okay. So the transition amplitude I can formulate in this way: take the overlap of I and f. Okay. Okay. And again, Heisenberg picture evolved this state using my Hamiltonian. This will be equals to this will be the same. I have to calculate. This is the transition amplitude, right? Now, if h is independent of time, then it's pretty much easy. But in general, h can depend on time. Okay, we don't need to restrict h is time independent. In any case, one way to calculate this one is we can try to split or slicing this amplitude. Okay, by that what I really mean is you can try to slicing. What I mean is you try to divide this entire interval into many slices. Okay, and you can try to evaluate each piece, each delta t. Okay? Because for each delta t, the h looks a constant, right? Then you sum up all the pieces. You get the result. So this means this will be equal to. So for each slicing, each dashed line, okay, for each slicing, I insert a complete set of position eigenstate. Okay, is that clear? In quantum mechanics, you can do that safely, right? Remember, for any, you can insert this in any. So this means that this will be equal to this dx. This x1 to xn is essentially denote these slicings. Okay, the slicings. And this is x up. This is e and h up. And xn. Dot x2. Same. Nothing of minus h. T2. Delta t. And then this y. And now there is e minus h1 delta t. And then I come there. It's hard. Okay. Okay. I did nothing but just slicing this time. Okay. Slicing this time. Then I insert any slicing. At each slicing, I insert a complete base of the position eigenstate, which is x. Okay. So because it's a complete base with a continuous variable, I have to integrate x. Okay. For x1 to xn, integral over delta x. Then this formula is basically slicing this whole transition amplitude, right, in quantum mechanics. Now, the next question is how to calculate it. Indeed, you can calculate this. You can calculate this one. Okay? It's not difficult. You can calculate it. Because for each such piece, you can calculate it. How to calculate this one? This is for each piece, right? How to calculate this one? You can try to insert again a complete base of momentum eigenstate inside this element. Okay? Then use your definition of the Hamiltonian. Okay? Because h is p squared over 2m plus v. Okay? That you have a h as an operator of both p and x. You see, right? Now I have p eigenstate. It's convenient for you to calculate this p squared term, right? So I have p squared over 2m plus v. V is an operator in terms of x, j, t, j. Okay, and delta t. Okay. This is all the calculate. Now this calculation you should be able to do it. It's easy. Because you can calculate this one acting on the left p state. You can calculate this one acting on the right x eigenstate. Okay, both are very easy. Okay, because this is the eigenstate. Then what you get is e to the minus I v x j dj delta t with the integral dt over 2 pi including minus 1 q squared over 2m delta t e to the 9 p x. This is the result. Okay, this is the result. Calculate it for you. This is the result. Okay. Then at that, I combine all the pieces. Okay. Take product of them together. Take product of them together. Now, of course, there's a p integral, but this p integral is a Gaussian integral. It's a very known, formula for this p integral. You use the Gaussian integral result. Gaussian integral result says if you do a p integral with something like this, what you should obtain is this one. Okay. You use this Gaussian integral result, then you obtain this this one. This will be equals to some prefactors times e v I m v xj tj delta t e to the I 1 over 2 delta t. Now I extract one delta t in front of them because this is this is delta t. Delta t is in the denominator, then there should left over twice delta t. Delta t squared. So this is the xj plus 1 minus xj squared. Okay, this will be the result out of this Gaussian integral. Okay, some factors I just factorize this out. Okay, this is the two important part. Now, key observation is what is this? This is the kinetic energy, right? Because now we do the continued limit, delta t goes to 0, right? When it goes to 0, this is what? This is v squared, you see? This is v squared. So this is the half m v squared, you see? And this is the potential. So kinetic energy minus potential is what? It's a Lagrangian, okay? This is a Lagrangian times delta t. So in the end, this will be equal to n times e to the I Lagrangian at the position x and x dot. We know Lagrangian is the function of x and the x dot. Let's schematically write it this way. This is the Lagrangian in the small piece, okay? In the delta t interval, okay? Then you put everything together. Because there are many pieces. You take a product of all these pieces of time. Then eventually, this will give you the final amplitude. Is some integral in this way. There are many Lagrangians. Okay, there are many Lagrangians. X1. Oh. There are many Lagrangians looks like this. Okay. Now, if you think about this carefully, this whole integral putting together. This whole integral putting together. This is what? This is a This include all the different parts. Okay, all the different parts. Okay, that this integral. Okay. So this is really equal to a path integral. This is equal to a path integral with the final position equals to x and the initial position equals to xi. With all the different paths weighted by a is, where s is the action. Okay, Think about it. These two guys are equal, okay? These two guys are equal. You see? It is just a matter of how you split or decompose a same object, right? You can think about it, for example, that from here, you can think about it here. You just slice it, okay? Because you sum up all the paths respect to the initial and final conditions is equivalent to you just slice in this way, okay? Okay? Just a matter of how you slice in your integral, right? Same thing. Slice in your integral. I want to do my integral. You can view in this way. You can also view in this way. Okay. That's the same thing. So this is the proof of the quantum mechanical path integral formula. The transition amplitude from xi to xf is equals to boundary condition. All the paths contribute with the weight factor is, where s is the associated action for the paths. Okay. 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 So, yeah, let's stop here. We will continue to discuss quantum field theory next time.
它那个 S 里面是什么？
一个球，L 的 LS 的，是那个吗？其实你也可以 N 是吗 ？N 是前面它那种圆形，哎，就往上朝，然后放弄它，然后再传过来，然后再盖上一个。我知道，那个圆形。那我看它这个黑板板上后面还有个。我是哪里？括号。母体了，你也是，反射。这是一种，然后说那个这个东西对一般是这个东西这像明确到但实际上这个在 DMP 里面是在非 DMP 中有没有就说或者说我们是吧？就它的微体是属于特别是还是为了找到这样的一个东西，找到这样的一个的话，那也行。咖喱东西是吧？没有它这个东西咖喱一个科是没有理。如果是个人东西，不是你知道吗？我这个他这个是问题嘛？我现在是不太理解 CM 这种一般的确，其他这怎么会是吧？很厉害。这个里边还复习到怎么？但是都上次总上，现在状态还好。不能说这这个东西如果是理的话，CMP 都是偏这个东西，因为这是 CMP 的。这个 CMP 不是可以 ，CMP 不是那个 T 是零的话是。AMU 是的，就是反正是这个是可以让它可以场在这里。它这个是。反正就是说，我就是那个，就是那个什么，那种就是。不是我操呀！我马上还要去大五实验，然后12:45来过。为什么大五实验？你又不能留着大四做吗？不是我胆他带你了，我直接跳了。那你不能跳，你要是学就不能跳。你学大概是它可以展成好几项嘛，但是像你对。但是就说如果你让我你这样对，让我你这样混起来的话，你就是已经成了。这个东西我给他搞，不是。如果能搞这个东西的话，那也可以试试看能不能写成更多的科目。要不然我搞不出来那么多科目东西，我都不知道。你
就写成这样，它有 load current 嘛，对不对？
对，
对吧？load current 一不行。
好，讲完了，你继续说看是不是？啊，你继续说看。
你上了。
你继续。